Time is not the same for everyone right now. Somewhere above Earth, time is moving slower for someone than it is for you. This is not science fiction, this is real physics. Astronauts orbiting Earth are already traveling into the future, not in some dramatic, cinematic way, not in giant leaps, but in tiny, measurable steps that scientists have confirmed again and again. While you sit here watching this, their clocks are falling behind yours, their bodies are aging just a little bit slower. The difference is small, almost invisible, but it is real, and here is where it gets unsettling. If you push this effect far enough, time does not just slow down, it begins to break away from everything you think it is. It stretches, it bends, it can almost stop. That means one simple, shocking truth. The faster you move, the slower time moves for you. And not just by a little, at extreme speeds, time nearly freezes. An astronaut traveling close to the speed of light could experience only a few years passing, while decades, centuries, even longer pass on Earth. They would return to a world that has aged far beyond them. People they knew would be gone. Entire generations would have lived and died. To them, it would feel like a short trip. To everyone else, it would look like they vanished into the future, and speed is only half of the story. Gravity does the same thing. The stronger the gravity, the slower time flows. Near massive objects like neutron stars or black holes, time becomes so distorted that the difference is no longer small. It becomes extreme. A person standing close to such an object could experience minutes while years pass far away. From a distance, they would appear to slow down. Their movements would stretch. Their voice would fade. Eventually, they would seem to freeze in time. From their perspective, everything feels normal. This is where reality starts to feel unstable. Two people, two clocks, two completely different experiences of time, both correct. That is the universe we live in. This idea comes from one of the most powerful theories ever created. Over a century ago, Albert Einstein revealed something that changed physics forever. Time is not fixed, it is not universal, it is not ticking the same way everywhere. Time is flexible. It depends on motion. It depends on gravity, it depends on where you are and how fast you move. And the most surprising part is this: we have already tested it. Highly precise atomic clocks placed on airplanes, satellites, and spacecraft show measurable differences. Astronauts on the International Space Station experience time slightly slower than people on Earth. The effect is tiny, measured in milliseconds, but it is undeniable. This means every astronaut who has ever gone to space has technically traveled into the future, not by choice, not by accident, but because the laws of the universe demand it. Most people never think about this. Time feels constant. Seconds feel identical. Days feel steady. Life feels like it moves forward at one fixed pace. But that feeling is an illusion. Beneath it, time is shifting all the time, quietly, precisely, following rules that are completely different from what human intuition expects. And when you push those rules to their limits, the results become extreme. Near the speed of light, time almost stops. Near a black hole, time can slow to a crawl. In the deepest sense, time is not a universal river flowing at one speed. It is more like a landscape that can stretch, bend, and twist depending on where you stand. This raises a powerful question: what actually happens to astronauts when time starts to slow down? What do they experience? What would you see if you were watching them from Earth? And how far can this effect go before time itself breaks down completely? Because this is not just about space travel, this is about the nature of reality. If time can slow down, then aging changes. If aging changes, then life itself changes. If time can almost stop, then the boundary between present and future starts to blur. And that leads to an even deeper realization. The universe allows travel into the future, not through machines, not through fantasy, but through motion and gravity. The faster you go, the further you move forward in time, the deeper you fall into gravity, the more time leaves you behind. This is happening right now, above your head, in orbit, quietly, consistently. Proven by science, yet still deeply strange. In this video, you will see how time actually behaves in space. You will understand why astronauts age differently. You will discover what happens as speed increases toward the ultimate limit. And you will explore what it means to stand near the most extreme objects in the universe, where time itself begins to break. By the end, the idea of time as a steady ticking clock will no longer feel real. It will feel like something far more fragile. Welcome to the channel. Subscribe now, because what you're about to learn will change the way you see time forever. Time feels steady. It feels the same every second of your life. 1 minute always feels like 1 minute. 1 hour always feels like 1 hour. But that feeling is not the truth of the universe. Time is not fixed. It does not move at one universal speed. It changes. And it changes based on two powerful forces, speed and gravity. This idea is called time dilation. It sounds complex, but the core idea is simple. Time can stretch or shrink depending on how fast you move and how strong gravity is around you. Start with speed. The faster you move, the slower time passes for you compared to someone who is still. This is not a trick. It is not an illusion. It is built into the structure of reality itself. If you could travel in a spacecraft at extremely high speed, your clock would tick slower than a clock on Earth, your heartbeat would slow, your aging would slow. Everything about your experience of time would stretch out. But here is the strange part. You would not feel any difference. To you, everything would feel normal. Your thoughts would move at the same pace. Your actions would feel the same. Your life would seem unchanged. The difference only appears when you compare your time to someone else. Now bring gravity into the picture. Gravity does something even more surprising. The stronger the gravity, the slower time flows. Near Earth, the effect is small. So small that humans do not notice it. But even here, it exists. A clock placed on the ground ticks slightly slower than a clock placed higher up in a building. The difference is tiny, but it is real and measurable. This means time is already moving at slightly different speeds around you, even right now. As gravity becomes stronger, the effect becomes stronger too. Near massive objects like stars, time slows down more. Near extremely dense objects, time slows down dramatically. This leads to a strange and powerful conclusion. Two people can live through different amounts of time, even if they start at the same moment. One person could stay on Earth, another could travel at high speed or move closer to a massive object. When they meet again, their clocks would not agree. Their ages would not match perfectly. One would be sly. This has already been tested with precise clocks and fast-moving aircraft. Scientists have measured the difference. Time itself shifted, so time is not a single shared flow that carries everyone forward equally. It is personal. It belongs to your path through space, your speed, and the gravity around you. Two people, two journeys, two different experiences of time, both completely real, and once this idea settles in, it begins to change everything that comes next. Right now, above Earth, astronauts are moving so fast that time is slipping behind them. They are not floating in stillness. They are racing around the planet at nearly 28,000 kilometers per hour. That speed is enough to circle Earth in about 90 minutes. Day and night pass again and again in a single shift. At that speed, something subtle begins to happen. Time slows down for them. Not in a dramatic way, not in a way they can feel, but in a way that precise instruments can detect with absolute certainty. Clocks on the International Space Station do not stay perfectly in sync with clocks on Earth. They fall behind. The difference is small. Measured in milliseconds, a fraction of a second spread across months of travel, but that tiny gap carries a massive meaning. It proves that time is not fixed. Every astronaut who has lived on the station has experienced this effect. Their bodies followed a slightly different timeline than everyone on the surface of Earth. Their hearts beat through fewer moments. Their cells age through slightly less time. They return just a little bit younger. There is a real example that makes this even more striking. An astronaut who spent nearly a full year in orbit came back to Earth measurably younger than his identical twin who stayed behind. Scientists compared their bodies in detail. The difference was small, but it was real and recorded. This is not theory and more. This is human biology shaped by the flow of time. And the story gets even more complex. Speed slows time down, but gravity pulls it the other way. Astronauts in orbit are farther from Earth's mass than people on the ground. That means they feel slightly weaker gravity, and weaker gravity allows time to move faster. So two effects are happening at the same time. Their speed tries to slow time down. Their position in weaker gravity tries to speed it up. These two forces compete with each other. In low Earth orbit, speed wins by a small margin. So overall, time still moves slower for the astronauts, but the balance is close. So close that engineers must calculate it with extreme precision. Satellites like GPS systems depend on accurate time to function. Even tiny errors can cause major problems. If scientists ignored time dilation, navigation systems would drift off course within hours. This means modern technology depends on the fact that time changes. Every time a satellite sends a signal, it carries the signature of a slightly different clock, a clock that lives in a different flow of time. So astronauts are not just exploring space, they are living inside a different version of time itself. Each orbit they complete adds another tiny gap between their timeline and hours they launch together with Earth's clock. They return with a clock that has fallen behind. The difference is small now. But it does not stay small forever. As speed increases, the rules begin to change faster than intuition can follow. At low speeds, the effect on time is small, barely measurable, but as velocity rises, the change does not grow in a straight line. It accelerates slowly at first, then more sharply, then violently as it approaches a final limit. That limit is the speed of light. Nothing with mass can reach it, but getting close is enough to push time into extreme behavior. At a large fraction of the speed of light, time for the traveler begins to slow down in a dramatic way. Seconds stretch, minutes expand, the flow of time itself begins to thin out. From the outside, something strange appears. An observer watching the astronaut would see their movements slow. Their actions would take longer, their clock would tick more slowly with each passing moment. As the speed increases further, this effect becomes stronger and stronger. Close enough to the speed of light, the change becomes almost unreal. The astronaut would appear to nearly freeze. Light coming from them would shift. Signals would stretch out. Their voice, if it could be heard, would drop lower and slower until it fades into silence. It would look as if time is draining away from them. But inside the spacecraft, nothing feels different. The astronaut would move normally, think normally, breathe normally, their heartbeat would stay steady, their sense of time would feel completely unchanged. This is the paradox at the heart of reality. Two observers see two completely different versions of time. Both are correct. For the astronaut, the journey feels short. For everyone else, it stretches into something much longer. Push this idea further, an astronaut travels at a speed so high that time slows to a fraction of its normal rate. They spend what feels like 5 years on their journey. They return to Earth expecting to see familiar faces, familiar places, a world that has barely changed. But Earth has not been waiting. Decades have passed, maybe more. Cities have grown. Technology has advanced. Entire generations have come and gone. The astronaut steps out of the spacecraft into a future that moved forward without them. This is not science fiction. This is a direct consequence of how time behaves at extreme speeds. It is a form of time travel, but it only works in one direction, forward. Third, there is no path back. No way to reverse the flow and return to the past. The faster you move, the more you detach from the timeline of everyone else. You drift ahead, carried by the very fabric of space and time. There's another detail that makes this even more unsettling. As speed increases, energy requirements grow rapidly. Near the speed of light, the energy needed becomes enormous, almost impossible to achieve with current technology, but the physics remains clear. If that speed could be reached, time for the traveler would slow to an extreme degree. From the outside, it would look like time is almost stopped. From the inside, it would feel like a normal passage of life. And that gap between these two realities continues to widen as speed climbs higher, pulling the traveler further and further away from the shared rhythm of time. Speed is only half of the story. There is another force that bends time in a quiet but powerful way. Gravity. Every object with mass pulls on space. Planets do it, stars do it, even you do it in a very small way. But when mass becomes large enough, the effect on time begins to grow. Time slows down in stronger gravity. This is called gravitational time dilation. Near Earth, the effect is small but real. A clock on the surface of the planet ticks slightly slower than a clock placed far above it. Scientists have measured this using highly precise atomic clocks. Raise one clock just a few meters higher and it begins to gain time compared to the one below. That means your head is technically aging faster than your feet. The difference is tiny, far too small to feel, but it is happening. Now, increase the mass, move closer to a massive planet. Then a star, gravity becomes stronger, the pull on space becomes deeper, and time responds. It slows down more. Near very massive stars, the difference becomes noticeable with instruments. Nay, our extremely dense objects, it becomes dramatic. There are objects in the universe where mass is compressed into a very small space. Neutron stars are one example. They pack more mass than the sun into a sphere only a few kilometers wide. Their gravity is intense. Close to their surface, time moves significantly slower than it does far away. A clock placed near such an object would fall behind rapidly compared to a clock in deep space. And then there are black holes. Here, gravity becomes so strong that it changes the behavior of time in extreme ways. As you move closer, time slows more and more. From a distance, the change looks strange and unsettling. An object falling toward a black hole appears to slow down. Its movements stretch out. Its light becomes redder and dimmer. It seems to approach a boundary and then never quite cross it. To an outside observer, it looks as if time is freezing. But for the object itself, the fall continues. This is the strange dual reality of gravity and time. Now, combine this with speed. An astronaut near a massive object is not only affected by gravity, they are also moving at high velocity as they orbit. Both effects begin to stack. Speed slows time. Gravity slows time. Together, they amplify each other in certain regions of space. This combined effect becomes powerful enough to create large differences in time flow. An astronaut could spend hours in such an environment while far away. Days or even longer begin to pass. There is a lesser known detail that makes this even more precise. Engineers who design satellite systems must account for both effects at once. Satellites move fast, which slows their time, but they are also farther from Earth where gravity is weaker, which speeds their time up. These two influences push in opposite directions, and both must be calculated with extreme accuracy. If even a small error is made, systems fail. So time is not only shaped by motion, it is shaped by where you are in the gravitational landscape of the universe. And as that landscape becomes more extreme, time itself begins to stretch in ways that feel less like a steady flow and more like something that can be bent, slowed, and nearly brought to a halt. At the edge of a black hole, time begins to lose its familiar meaning. Gravity there is not just strong, it is overwhelming. Space itself is pulled inward, and time is dragged along with it. As an astronaut moves closer, time slows more and more. Not slightly, not gently. It slows in a way that becomes impossible to ignore. From far away, the change looks almost unreal. A distant observer watching the astronaut would see their motion begin to stretch. Every movement takes longer. Every signal arrives more slowly. The closer the astronaut gets, the more extreme this effect becomes. Then something even stranger happens. The astronaut appears to fade. Light leaving their body has to climb out of the intense gravity. As it escapes, it loses energy. Its color shifts toward red. This is called gravitational redshift. The light becomes weaker, dimmer, stretched across longer wavelengths. To the observer, the astronaut grows darker and slower at the same time. Their clock seems to tick at a crawl. Closer still, the astronaut appears to almost stop. Frozen, held at the edge of time. Signals from them take longer and longer to arrive. A message sent every second turns into one that arrives every minute, then every hour, then longer. Eventually, the gap becomes so large that communication fades into silence. From the outside, it looks as if the astronaut never fully reaches the boundary, as if time itself is holding them back. But inside that experience, nothing feels frozen. For the astronaut, time continues to move forward at a normal pace. Their heartbeat remains steady, their thoughts remain clear, their actions feel unchanged. They cross regions where outside time is stretching wildly, yet their own sense of time stays consistent. This creates one of the most extreme contrasts in physics inside a normal flow of life. Outside, a universe that is speeding ahead. As the astronaut approaches the edge, something profound begins to unfold. The outside universe appears to move faster and faster. Events that would normally take years begin to pass in shorter and shorter moments. Distant stars shift, galaxies evolve, the sky itself begins to change at a rapid pace. Time outside accelerates. In theory, if the astronaut could hover close enough to this region, the effect becomes extreme. Minutes for them could correspond to years far away. Stay longer, and those years could stretch into decades, even centuries. The universe would age in fast motion beyond their reach. Civilizations could rise and fall while they remain near the same moment. There is a lesser known detail hidden in this scenario. The closer you get, the more energy is required to stay in place. Holding position near such intense gravity demands enormous power. Without it, the pull becomes unavoidable. And once that pull takes over, the journey continues inward. From the outside, the astronaut never seems to cross the final boundary. From the inside, the crossing happens without pause. Time, once steady and reliable, now splits into two completely different realities. When time slows down, it does not only affect clocks, it affects the human body. Every process inside you follows time. Your heartbeats, your breathing, your thoughts, the way your cells divide and repair, all of it moves forward second by second. Change the flow of time, and all of it changes with it. If time slows for an astronaut, their biology slows too. Their cells take longer to age. Chemical reactions stretch out. Even damage inside the body progresses more slowly. From the outside, this looks like a form of delayed aging. It is not immortality, it is not stopping death, but it is a shift in how quickly life unfolds. Astronauts on the International Space Station already experience a tiny version of this. Their aging is slightly reduced compared to people on Earth. The difference is small, measured in milliseconds of life, but it proves something powerful. Aging is tied to time, and time is not fixed. Push this effect to extremes, and the consequences grow far beyond small differences. An astronaut traveling at very high speed or spending time near intense gravity could experience far less aging than everyone else. Their body would move through fewer moments, while the rest of the world moves through many more. To them, the journey feels normal. To everyone else, they seem to pause in time. This creates a strange kind of future travel, not by skipping forward in an instant, but by letting the rest of the universe race ahead. An astronaut could leave Earth for what feels like a few years and return to find that decades have passed. People they knew would be older. Some might no longer be alive. Places would change. Languages, technology, culture, all of it could shift. The traveler would feel out of place, not because they changed too much, but because everything else did. There is a deeper psychological effect hidden here. Human identity is built on shared time. People grow together, they age together, they experience the same world at the same pace. That shared timeline creates connection. Break that timeline and something feels lost. An astronaut returning from extreme time dilation would carry memories from a past that no longer exist in the same way. Their reference points would be outdated. Their sense of belonging could weaken. They would be physically present but slightly disconnected from the flow of the world. There is also a quiet biological detail that adds another layer. The human body is adapted to Earth rhythm, day and night cycles, gravity, environmental stability. Long exposure to space already causes changes in muscles, bones, and even DNA expression. Add time distortion to this, and the body begins to operate under conditions it was never designed for. The result is not only physical strain, but a shift in how life itself is experienced. And beneath all of this lies a deeper question. If two people live different amounts of time, who has truly lived more? If your clock runs slower, does your life become longer in a meaningful way, or does it simply separate you from everyone else? Time, once seen as a shared path, starts to feel personal and fragmented. Each person moving along their own version of it. And as these differences grow larger, the gap between those timelines becomes impossible to ignore. Time feels steady. It feels reliable. It feels like something that moves the same for everyone. But it does not. Time bends. It stretches. It slows down under speed and gravity. It changes depending on where you are and how fast you move. Astronauts are already living proof of this. High above Earth, their clocks fall behind ours. Their lives unfold just a little bit slower. The difference is small, but it reveals something much bigger. Time is not universal. Push this idea further, and the effect becomes extreme. At incredible speeds, time nearly stops. Near massive objects, it slows to a crawl. Near a black hole, it almost breaks apart completely. Two people can start at the same moment and end up in completely different futures. One lives through years, the other lives through minutes. This is not theory. This is how the universe works, and hidden inside this truth is something even more powerful. The universe allows time travel, not backward, never backward, but forward. Every step toward higher speed or stronger gravity pushes you ahead, away from the shared present, into a future that arrives faster for everyone else. This changes how we see everything. Aging is not fixed. Time is not absolute. Reality is not as stable as it feels. The deeper we explore space, the more these truths reveal themselves. And the more we realize that time is not a simple line moving forward, it is something far more flexible, far more strange, and far more powerful than we ever expected. If this changed the way you see time, take a moment to like the video and subscribe to the channel for more explorations into the deepest ideas in science and space. Because the next discovery might not just change what you know, it might change how you experience reality itself.